Let us consider the second example. Here we have to discuss the convergence of the series summation bracket n plus 1 by n minus bracket n plus 1 by n whole to the power n plus 1 whole to the power minus n. So here also the given series is in the direct form, that is standard form, that is summation un. Therefore we can directly write down that here un is the bracket n plus 1 by n in the first bracket minus n plus 1 by n whole to the power n plus 1 whole to the power again minus n. So this is the nth term of the given series, and we observe that whenever un contains whole to the power n, we are advised to apply the Cauchy's root test, and the principle of the Cauchy's root test involves the first job, that is to take the nth root, that is we have to rise on both sides by the power 1 by n. So here whatever is this, on that we have to rise the power 1 by n. So let us keep this thing as it is within the bracket and take whole to the power 1 by n. That we have done. So we are writing the bracket as it is. So it is n plus 1 divided by n whole to the power n plus 1 to the power minus n. And now it is simple, we have to use the properties of indices. This is a, just like a to the power m whole to the power n is nothing but a to the power of m into n. So that property of indices, when we use minus n into 1 by n, n cancel, it is minus 1 remaining. So it is, after simplification, n plus 1 by n, this bracket, first bracket, minus the second bracket n plus 1 by n whole to the power n plus 1 as it is. Now close this bracket, and to the power n when cancelled, remaining thing is minus 1. So the power is minus 1 remaining now. Now let us write this term as, the first term is n plus 1 by n as it is, minus this is just like a to the power m plus n, can be written as a to the power of m into a to the power of n. So it is the bracket to the power n into the same bracket to the power 1. So again, by using the properties of indices, we are writing this whole to the power n plus 1 as bracket to the power n into bracket to the power 1, and here we are having power minus 1 at the end. Now here we are observing the bracket, this particular bracket is common, and that bracket can be taken outside. So it is n plus 1 by n. When we take it common, we will be having within the bracket, here 1 remains, minus here this thing remains, that is n plus 1 by n whole to the power n. So close this bracket and the square bracket as well, to the power minus 1 remaining. Now we have to take the power minus 1 onto this term and onto the second term. So let us take the power onto the first term, that is n plus 1 by n whole to the power minus 1 into the bracket 1 plus n plus 1 by n whole to the power n and its power minus 1. So we have taken the exponent on the two terms separately. Sorry, this is minus sign, I have to correct it here. This is minus. So this is the term. So the value on the right hand side is un to the power 1 by n. So we were finding the value of this, we simplified and got this answer. We can observe here. We have started with un to the power 1 by n, and we are able to get the answer as this thing on the right hand side. Now, according to the root test, we should take limit as n tending towards infinity of un to the power 1 by n. So we have to take limit on both sides as n tending towards infinity. So it is limit n tending towards infinity of the first term, that is n plus 1 divided by n whole to the power minus 1, into the bracket here as well 1 minus bracket n plus 1 by n whole to the power n, close the bracket and take its power minus 1. Before applying the limit, it is better if we simplify this. That is, we can separately divide and simplify this, and we can simplify this term also in the same way. Therefore, we will be getting this is equal to limit as n tending towards infinity of bracket n by n is 1 plus 1 by n separately divided and got this much within the bracket and whole to the power of minus 1 as it is, and here also this bracket 1 minus, and within this thing we have to separately divide n by n is 1 plus 1 by n is remaining thing here after separate division and whole to the power n this as it is, and close this bracket, keep this minus 1 exponent as it is. Now it is the time to apply the limits. So when we apply the limit onto this, that is when we put n equal to infinity here, so the first term will be 1 plus 0, because 1 by infinity is 0, 1 plus 0 whole to the power of minus 1 as it is, and here within the bracket 1 as it is minus limit of this thing is one of the standard limits. Again we have to use the formula limit as n tending towards infinity of 1 plus 1 by n whole to the power n. This is one of the standard results we have been using. So according to that, the value of this standard limit is the exponential constant e. So let us use that value over here. So it is simply e. The value of this limit is e as n tending towards infinity. Close the bracket and take the exponent minus 1 as it is. Now this is equal to 1 to the power of anything is 1 into the bracket 1 minus e can be written as 1 minus 2.71828 dot 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 its power minus 1. So it is 1 into this bracket is the same bracket 1 minus 2, 1 minus 2 point something is minus 1.7182 dot 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 its power is minus 1. So anything to the power minus 1 can be written as 1 divided by that value, that is minus 1.7182 dot dot dot. So 1 divided by this quantity, and even it is negative quantity, of course it is less than 1. This value is the limit so obtained is less than 1. So by the principle of root test, we can now conclude that the given series summation un is convergent, because when the limit value is less than 1, the series is convergent. So this completes the solution of the second problem. Let us move on to the third problem. So in this problem we have to test the convergence of the series 1 plus 1 by 2 into x plus 2 by 3 whole square into x square plus 3 by 4 whole to the power of 3 into x cube plus 4 by 5u to the power 4 into x to the power of 4 plus dot dot dot. Here we are observing that the first term 1 we can ignore here for our convenience, because the variable x, which is given to be positive, is appearing from the second term onwards. That is, in the second term its power is x to the power 1, in the third term its power is 2, in the fourth term its power is 3, and so on. And in the first term it is absent. Therefore it is necessary here and it is convenient here to ignore the first term in the given series. When we ignore the first term of the given series, the series becomes summation un equals to 1 by 2. For example, 1 by 2 to the power 1 we can write, and x to the power 1, plus the second term is 2 by 3 to the power 2 into x to the power 2, plus 3 by 4 to the power 3 into x to the power 3, plus dot dot dot. So in general, from this we can write un equal to, we are observing here, for the first term it is 1, for the second term it is 2, for the third term it is 3, for the nth term it should be n, and the denominator, it is, for the first term it is 1 plus 1, for the second term it is 2 plus 1, for the third term it is 3 plus 1, for the nth term it should be n plus 1. So we have written this bracket to the power. For the first term power is 1, for the second term the power is 2, for the third term the power is 3, for the nth term the power must be n, and into x. For the first term power is 1, for the second term power is 2, for the third term power is 3, for the nth term the power is n. So this is the nth term of the given series, and according to the ratio test we have to take the nth root of un, that is un to the power 1 by n we have to consider. So therefore it is n divided by n plus 1 to the power n, x to the power n, un we have kept as it is, and we are raising by the power 1 by n. Now according to the principle of indices, we can take this within the bracket, and then we will be getting n by n plus 1 to the power 1, because n into 1 by n cancel, 1 remains. Similarly, x to the power n whole to the power 1 by n, n cancel, x to the power 1 remains. So this is the thing remaining. Now we have to take limit on both sides. Therefore limit as n tending towards infinity of un to the power 1 by n, that is equal to limit as n tending towards infinity of n divided by n plus 1 into x. X is independent of n, therefore it can be taken outside the limit. So x into limit n tending towards infinity of, now we observe that here in the denominator it will be convenient if we take n outside. So before taking the limit we have to simplify, so we are taking n outside. When we take n outside, here 1 remains, plus here it is 1 by n remaining. So this is the thing, and we can cancel this n with this n. So now when we apply the limit, x into 1, it is x remaining here, divided by, when we apply limit here, it is 1 plus 1 by infinity is 1 plus 0. So the answer is x. So the value of the limit we obtained is x, which is a variable, and it is given to be positive. Now there is chance of having x greater than 1, x less than 1. Therefore by the root test we can conclude that the given series summation un converges for this limit. Value of the limit here is x. If that limit is less than 1 and the series summation un, the given series, diverges for the value of the limit is greater than 1, that is x greater than 1. So these are the two possibilities we are having over here. But when x is equal to 1, the root test fails. This is the conclusion we have to draw here. The root test fails, and in that case we are advised to apply another test, either fundamental test or the so-called comparison test. Now for x equal to 1, we have to put this particular value into the expression of u. For x equal to 1, un is equal to, what is the definition of un? What is the form of un we are having here in this problem? Un is equal to n by n plus 1 to the power n into x to the power n. In this place, if we put 1 to the power of n is 1. So only this much is remaining. That is n divided by n plus 1 whole to the power n. So un value is n divided by n plus 1 whole to the power n is remaining. And let us simplify this. So if we simplify, it is going to be n divided by, we can take n common from the denominator so as to have 1 plus 1 by n, 1 plus 1 by n, that is, and we are having whole to the power n. Now this n cancels with this n, therefore un is 1 to the power n is 1 divided by, in the denominator we are having 1 plus 1 by n to the power n. So this much we are having for un. Now it is convenient here in this case to apply the fundamental test. Therefore we have to take limit of un as n tending towards infinity. Therefore on taking limit on un as n tending towards infinity, on RHS what happens? Limit as n tending towards infinity of 1 divided by bracket 1 plus 1 by n to the power n. And we observe here that 1 as it is, whereas when we apply the limit here in the denominator, it is one of the standard limits. I have told you in the previous problem itself, its value is the exponential constant e. So it is 1 by e, and we know that e value is 2.71828, something like that. So it is 1 by something, 1 by 2, and this value is non-zero, and therefore when the limit of un as n tending towards infinity is non-zero, that is what we got here, limit of un as n tending towards infinity is, we obtained it as non-zero. Then the fundamental test of convergence implies that the given series summation un is divergent. This follows by the fundamental test of divergence. One can refer my second video on infinite series for this fundamental test of divergence, what it is actually. We proved that when the given series is convergent, limit of nth term is 0, and the contrapositive form of that statement gives us the fundamental test, and that fundamental test tells us that when limit of un is non-zero, then the given series is divergent. That we have done over here, that we have used over here, and concluded that for x equal to 1, the given series is divergent. So hence we can conclude at the end, the given series summation un is either convergent or divergent. So it is convergent for x, that is the limit value x less than 1, and it is divergent for the limiting value x greater than 1, and also in this previous case we have observed that even when x is equal to 1 the series is divergent. So this completes the solution of the problem, and this is how we have seen how can we apply the root test to determine the nature of the given series of positive terms. So in the next video, we shall consider the alternating series, that is the series with alternatively positive and negative terms. So please watch the next video. Thank you.